All right, welcome back. We're going to do what now is going to be for sure the last installment of chapter 1, and that's going to be scientific method. So scientific method was this idea where we need to have proof. If you have a great idea, great. Just show us some evidence that your idea is as great as you think it is. And this was not the case for a very long time. If you remember from, say, 400 BC, there was Democritus that said that the world was made up of atoms, and people said, sure, for about 100 years. And then Aristotle said, yeah, I think the world is made up of atoms too. I don't think they can be divided any further. And for 2,000 years, there was no challenge to this idea. Very few people even worked on it because they said, well, Aristotle was a smart guy and he must have knew what he was talking about. So eventually in the 1600s, lots of ideas were coming about, and eventually Robert Boyle, an Irish philosopher, chemist, and physicist, said, enough is enough. Prove your ideas, or they're just ideas. They're not going to be useful to the scientific community. So he wrote a book in the 1600s called The Skeptical Chemist. For this, he was considered the father of scientific method, and really the founder of modern chemistry, in the sense that he gave us a reason to experiment. He gave us a process of how to experiment in order to get progress in this scientific method idea. So experiments are things that we do in class. We're going to do about 24 of those, either face-to-face or virtually, depending on the semester and depending on your section. But really what we're after is trying to explain why laws in the nature exist. So why, when you throw an apple in the air, does it come back to Earth? Those are kinds of ideas that were figured out through experiments, through the scientific method, so to speak, as a process. So in the scientific method, you have some kind of experiment where you collect data, then you have to interpret that data, and then do more experiments. That kind of goes round and round and round, and we do have direct practice of this in our second experiment. Something that all scientific methods have is a hypothesis, this original idea that has to be tested, so then you experiment on it. Eventually, after years and years and years of hypotheses that are being experimented on, that are now getting data and say results, and then eventually what we have is maybe what's the theory, if it continues in that same kind of general direction. So not every hypothesis will make it to a theory. Only if they're a hypothesis that's good, kind of tried and true through years of experiments, do we actually get to a theory. And the job of a theory is really to kind of summarize or interpret what a law really is. So it's kind of summarizing that idea. So again, what is the relationship between a theory and a law? Well, a theory should kind of explain a law. It should tell us why things melt, why things go up in the air and come back down. It's understanding those ideas of what atoms are doing. There's a lot of cases where chemistry comes back to that being that central science kind of topic. And then what is the difference between a law and experimental data? Well, it's really just a summary. So you're summarizing a law by experimenting on it. The interpretation of those experimental results, of that summary of results, is how a theory is going to try to explain a law. So theories explain laws. That's the idea you'll see on the final exam. You'll see it in chapter 1 as well. Some of the problems with scientific methods comes back to what we talked about in an earlier video. Science is only as good as the scientists. So the flaws in experimental design oftentimes come with money, because money is the root of all evil in many cases. And when the money runs out, so do the experiments. So looking at, how to understand scientific method and its limitations is really just about how much you test. If you want to know what happens to a pharmaceutical drug, if you want to give it to 10 million people, you should test 10 million people. The problem with testing 10 million people is you'd have to pay those people to come in, you'd have to probably feed them, you'd have to have people to watch over them in case there are side effects, and that's going to be very expensive. And if it's too expensive, that company's not going to make any money, and there is no company that wants to, do everything for free. So companies are there to make money. So what they're going to do in many cases is try to use a model, try to give a representation of what they think is going to happen by testing, say, 10,000 people. If they test 10,000 people, will they know what's going to happen to 10 million people? Well, no. And that's the disadvantage of science, is it comes down to money. There's no way to think of every possible outcome without testing all possible outcomes, right, on all possible people. So whether it's a vaccine or, any kind of medicinal kinds of things, there's going to be, side effects. And that's something that they may or may not see depending on how much money they spend. So oftentimes in more modern scientific method kind of falls short because of money. And then the last one is a little bit more of what you think about with a jury. There could be bias. So if they really want a drug or a pharmaceutical to go out on the market, what they would likely do, which wouldn't be very ethical, would be to test a population or test a group where they would know the results beforehand. If they know the results beforehand, it's like picking the best juror from a jury panel. You want the people on that jury to have some kind of characteristic that's going to, be to your benefit, to be to your, to your clients or your defendants' benefit, so to speak, or vice versa if you're the prosecutor, for their to their benefit. So for an example, it would be if you were to have a new drug that cures menstrual cramps, you could test a bunch of men and their menstrual cramps are cured. And that's a great way to get the results you want. But will you have any idea what happens to a bunch of women that would actually have menstrual cramps? No. And that's how we could use an impartial kind of jury or an impartial group of participants to get the results that we want. In this case, that would not be ethical. And it would not be helpful either. It would be pretty dangerous. So as we kind of close this chapter, we have to think about what we learned. My hope is that you look at things like ice melting and you see that it's not quite that simple. So as the example that we'll see here, ice is really trillions and trillions and trillions of little H2Os. H being an atom, oxygen being an atom. There's 2 hydrogen atoms, 1 oxygen atom to make the molecule of water. But there's trillions and trillions and trillions of those water molecules held together by intermolecular forces, which is like glue. That glue is holding them into that solid form. And we can physically change that solid form by weakening the glue with heat, by warming the ice cube up. And when that heat weakens the glue, we now see water in a new form, a new physical form, liquid. So even ice melting is pretty complicated behind the scenes. And that's kind of what we're after in this overall course is some things might seem simple, but they're actually very complicated behind the scenes, as is the case for ice melting. So see you for chapter 2.